In this second video segment, we are looking a little more in detail in this contact and the constraints that these contacts impose and how this has an influence on the motion capability of our system. Now, there's two special things about floating base systems. The first special thing is that the floating base is described by base coordinates, which define the position and the orientation of the base frame. And these base coordinates, as we know, they're not actuated. So that means I cannot freely move the base in space if I'm not in contact with the environment. And this brings us to the second important element about floating base systems, namely that they interact with the environment through a number of contact points. And these contact points, they impose constraints. And as we learned, these constraints, they're again related to Jacobians that are taken at these points in contact. And only if we have a certain number of constraints, we can move the base through these joints. So I can actively move these joints. And since I'm having constraints here, I'm actually moving the base. And all of that, how this relationship between whether or not the base is movable and to what extent we can control this motion, this is all a function of this stacked contact Jacobian. And this is what we do here. We analyze this a little more in detail and figure out what kind of relationships that have to be satisfied in order to make the systems fully controllable. To analyze the controllability of the base, we have to analyze the properties of the contact Jacobian. And to this extent, we have to split this contact Jacobian into two subcomponents, a subcomponent which is only depending on the base coordinates and a subcomponent which is depending on a joint coordinate. So in other words, we have a constraint, so dr with respect to the QB, so with respect to the base coordinates, and the same constraint with respect to the joint coordinates. And if we look at this first Jacobian in here, then this tells us the relationship between the base motion, so this QB, and the constraint, this RC. And if I analyze this rank of this JCB, this tells me to what extent the constraints allow the joints to directly move the base. If the rank of this JCB is full, and that means for a 3D system rank equal to 6, then the base is fully controllable. If it's not full, then certain degrees of freedom of this base remain uncontrollable. There's a second interesting element that we see in here, namely that the rank of JC, this tells me the total number of independent constraints. And this minus the rank of JCB, so the number of constraints that essentially contribute then to motion of the base. So this difference in here, these are the number of kinematic constraints that have to be satisfied for the joint actuators. And I try to illustrate this with a simple example here. So assume that we have a robot with 4 actuators, a very simple robot, in 2D space, and this robot is in contact with the 2 point feet with the environment. Then what we have in here is a Q base, which is equal to x, y, and an angle alpha. And we have a Q joint, which is equal to phi 1, phi 2, phi 3, and phi 4. So 4 degrees of freedom of the joints. And we have a constraint. We have a JC, which is a matrix R4 times 7. So we have 4 constraints they're linearly independent, and we have 7 Qs, so 7 degrees of freedom in my system, which has a floating base. Now for this specific system, if I analyze my JC, the rank of JC, then this rank is equal to 4. Now it's a little more tricky to analyze the rank of JCB. We would have to go into the calculation of the individual Jacobians and then analyze the rank of that. We don't want to do this. We rather look at this from a intuitive perspective. Assume that we lock these 2 feet to the contact. So we have here 0 velocity and here 0 velocity. Then, like, our intuition clearly tells us, by moving these 4 degrees of freedom, I can arbitrarily change the height of that point, I can change the x position of that point, and I can change the alpha of that point by just changing these 4 angles. So that means the rank must be full. So we have here -3. So if I take 4 minus 3, this results in 1. So that means we have one constraint that has to be satisfied when moving these 4 actuators. I cannot arbitrarily move these 4 actuators, otherwise I would violate the constraint. And this constraint says that these 2 points here, this distance here, has to remain constant. So it's a one-dimensional constraint, in fact. In the other 3 directions, if I move it, then what I do is I change the height, I change the position, and I change the angle of the base. So that means that I directly influence, by moving the 4 degrees of freedom, I influence through the constraint the base motion. Now there's one last thing that I want to mention here, namely that generalized coordinates, they don't correspond to the degrees of freedom of the system. So this system that we have up here has 7 generalized coordinates, but for constraint there are 3 degrees of freedom how the system can move, and there is 1 internal constraint, and all of that is determined by the contact constraint. If I would want to avoid this, that I have constraints and generalized coordinates, I would have to move to minimal coordinates, which then really corresponds to the number of degrees of freedom that I have in my system. But for floating-based systems which interact with the environment at different locations at different times, that would require to switch the set of coordinates depending on the contact state. So this is, in practice, this is really never used. Now we're looking at this in a little more detail with a simple example of a cart pendulum, the cart pendulum that I displayed here on the right hand side, which has in essence 2 degrees of freedom, so 2 generalized coordinates, x and phi, while x is the base coordinate. The base coordinate is equal to x, and we have 1 joint coordinate which is equal to phi. Then we have 1 actuator which is actuating this joint coordinate phi. And what we have to do is we have to analyze the kinematic constraint of this example. We're looking at 3 different scenarios. First one, that this point P here cannot move at all. Second one, that P can only move horizontally. And third one, that P can only move vertically. So let's start with the first one. The first one, so P cannot move at all, which means I lock this to the environment. So I have to look at the position of P, and this position of P must remain constant, so the velocity of point P must be 0. So we write first the position of P, so we go by x and this 2L cosine phi, 2L sine phi in x direction, and we go by minus 2L cosine phi in y direction. P cannot move, so the velocity of point P equals to 0. We take the time derivative of this P up here, RP up here, and set this to 0. That gives us the Jacobian, and we can split the Jacobian in a base Jacobian and in a joint Jacobian. So you have the base Jacobian here, and you have the joint Jacobian to the right of it. And then we analyze the rank of these Jacobians. If we analyze the rank of JC, we have rank 2. If we analyze the rank of JCB, we have rank 1. Now, what is the interpretation of this? So the first interpretation is rank JC equal to 2. That means my constraints are two constraints, two linearly independent constraints. So 2 degrees of freedom are blocked by this P. And since Q is only 2-dimensional, all 2 degrees of freedom are blocked. In other words, by fixing it at point P, the system is not allowed to move. Just for completeness, I mean, what I see here is essentially a system that looks the following. It can only move in X direction. It can also not rotate or also not lift off, just for completeness. The second thing we see here is that 2 minus 1 equal to 1. So I have one constraint which is imposed on my joint level degrees of freedom. In other words, the actuated degrees of freedom is not allowed to move. So with my tau A that I have here, all I can change is the interaction force at this point P, but I cannot change the motion of the system. All right, then let's move on with the second example. P can only move horizontally. So what does that look like now? We have P that can only move horizontally. So we have here essentially a system or a constraint that looks the following way. It can only move in X direction. So what does that mean? That means that Y dot, so this second line here, must be 0, and hence the contact Jacobian looks the following way. I have a JCB, so the base part of it, which is 0, and I have a JCJ, which is 2L sine phi. If I analyze now the rank of this Jacobian, I see that the rank of JC is equal to 1, and the rank of JCB is equal to 0. What does that mean? That means JCB equal to 0 means, well, this constraint does not allow me to modify my X, my base coordinate. So I have no handle on my base coordinate. So, and that's actually true. So whatever I do here, I can still move this whole setup in X direction. I can still move in X direction independent of that constraint. That's why this is 0. So I cannot determine or change the motion of the base thanks to this constraint. The first one, JC1, means it's only a one-dimensional constraint, and if I take 1 minus 0, which is equal to 1, that means I have still one constraint on my joint, on my phi, which means that I cannot arbitrarily move phi without violating the constraint, which is also obviously clear. So I can move the cart here, but I cannot move this pendulum around this axis. Now the third constraint is then a different one. So the third constraint here looks the following. We have now a cart which can move only in Y direction, so we can move in this direction. That means this X dot must be 0. So I have my X dot of P must be 0. I can determine again my contact Jacobian, which has a base part in here. And if I analyze the rank of that now, I have JC, the rank of JC equal to 1, and the rank of JCB equal to 1. So what does that mean now? That means my constraint in essence, allows me to determine the x. And in fact, that's true. So given the current configuration, through the phi and the constraint, I can move my system in x direction. And if I take 1 minus 1, this is equal to 0. So that means I can, in this situation, I have no constraint acting on phi. I can flexibly move phi, but by moving phi, what happens is that, for example, if I move phi in this direction, this constraint moves up and that card moves back. So by moving phi, I can modify my x without violating constraint, and there is no constraint on phi. So this is equal to 0. I can change my base and have only one constraint in total that is active. And what we did here for a very rudimentary or simple example, we can now apply to much more complex systems. For this, we have prepared a small quiz with a quadruped. Quadruped that is in different configurations. So one is in the air. Then we have everything in the air except for one contact, which is 1 foot, which is in contact with the environment. This is only a point contact, so it can just not move in X, Y, and Z direction. Then we have the 2 diagonal pairs of legs, the 2 diagonal legs in contact. Then we have 3 legs in contact, and then we have all 4 legs in contact. And what I ask you to determine for this, without going through the Jacobian calculation, just from an intuition point of view, what are the total constraints, what are the base constraints, the internal constraints, and then how many degrees of freedom remain uncontrollable.